The 8 queen problem is a great test of your algorithmic thinking and optimization skills. So let's give it a go. Hi and welcome to Bytes and Bits. The 8 queen problem is where we take a chessboard and we're trying to place 8 queens on that board so that no 2 queens are attacking each other. And what we have to do is we have to write a computer program that will search through all the possible combinations of placing queens on the chessboard and give us back the solutions which give us this situation where no queen is attacking another one. So really it's a test of how well you can turn this into an algorithm and then refine that algorithm and optimize it so that it actually can complete the task within a reasonable amount of time. So let's have a look at the problem and see how we can get to a solution. So just to make sure that everybody understands the problem, a chessboard is a grid of squares, so 8 by 8, which gives us 64 squares. And a queen is one of the chess pieces, but this particular piece is one of the strongest pieces on the board. If we place it on a square, then the queen is able to attack horizontally, vertically and diagonally. So we can't place other queens in any of these positions relative to this queen. So if we put a queen here, we can place queens in these 3 positions, but then not in these 3 positions. So our challenge is to find all the possible ways that we can put these 8 queens onto the board, and then to test each of those possible solutions to see if it works. If it does, we've found a possible combination. If not, then we have to try the next one. So if we think about the total number of permutations for this, there are 64 squares we could possibly place the first queen into, then 63 for the next queen, 62 for the third queen, and all the way down to the 8th queen where we'll have 57 possible ways of placing it. And this gives us quite a number of permutations. But if you remember back to your maths lessons, it's not the permutations we want, because it doesn't matter what order we pick these squares in. It's actually the number of combinations we need, so we have to use this mathematical NCR function. And this drastically reduces the number of possible board layouts that we have to test. But that's still quite a large number. So say we were on a reasonably powered computer and we could test 50,000 board layouts per second. Well, that still gives us 24.6 hours to process this problem, and that is a bit too long. So we really need to take a look at the problem and have a look if there are certain ways in which we can rule out a number of possible combinations. We'll then have to design our algorithm to take these optimizations into account to try and reduce this number of possible solutions that we have to trawl our way through and work out. So let's have a look and see what optimizations we can make. If we look at how we place our queens, well, let's say we're going to put our first queen in the very first square. Well, putting a queen on that first row anywhere really means that we can't put any other queen on that row. So in fact, each queen will have to go on a separate row. And what this means then is that when we place our first queen, we can put her on the first row in one of 8 positions. The second queen then has to go on the second row, and again she can go in one of 8 positions, and that can carry on all the way down our grid. So in effect our number of possible combinations now is simply 8 positions for the first queen, 8 for the second, and so on. So that's 8 to the power of 8 combinations, which is just under 17 million. But that is an awful lot less than we had of possible combinations using the full 64 square grid. So our algorithm is basically going to place a queen on the first row. It will then place a queen on the second row in a safe position. a queen on the third row in a safe position, and carry on down. But the way in which we're going to define whether it's a safe position or not is we're going to start always in column number 1, try a queen there, and then have a look at where the queens above it are. And if any of those are in an attacking position, then this position isn't safe. What that also means for us then is that once we find an unsafe position in one of the rows, then we don't need to check anything beneath that, because this particular combination of queens down to the red queen on the screen at the moment, then anything using that combination is invalid no matter where the other queens happen to be. So we suddenly block off a whole range of options that we need to check. And in fact, on this line, if you look at how many positions can't be used for this queen, then you can see how many possible combinations we actually just blank off simply because the first positions don't work. Okay, so let's have a look at building up this algorithm then. And we'll do it using some sort of pseudocode, which will let us see the structure that our end code's got to have. Now we know that we are really taking each queen and then placing one on each row. So our methodology will be to put a queen on the top row, which will be row 0. Again, we're using zero based indexes here. So row 0, we'll put it in position 0, so that'll be the top left hand corner. And then really we're then going to try and place a queen on the second row, and then after that on the third row. But each time we will simply be looping through each of the positions to find the first safe position. So as we're going through them, we'll start to build up a list of safe positions for each of our queens. So our first thing is we will need to sort of have some sort of storage to hold our current solution. So really if we create an array which has 8 elements in it, and then in each of the elements in that array, we will store the column position of our safe position. So again, the index number will give us the row, and the value contained in that index will give us the column. So really then, if we start thinking about our row 0, so we know that we are going to be counting and testing from column 0 up to column 7, and this will be the column value for our row 0. So we end up just having a simple for next loop. Okay, so let me just put in the next column 0. And really what that does then, we will try putting a queen in column 0 in row 0. And really, because we're on row 0, then every single position is actually safe. Okay, so really all we need to do is we need to store this current column 0 value that we're testing inside our current solution. So we just simply use that assignment. Then we need to start looking at our row number 1. And again, we're going to be doing pretty much exactly the same thing. So for our row 1, well, again, we're going to start off putting a queen in position 0, in column 0, column 1, 2, 3, 4, 5, 6, 7. And for each of those, we're going to test if that is a valid solution. So let's just put in our matching next for that so we don't get mixed up with where we are. So we know we have that in our code. So we now need to check. So we will be testing each of these index values, each of these columns, to see if we have a safe position. So really all we're doing is we're saying if it is safe to put a queen in row 1, so in other words we're in row number 1, and the column 1 value that we're currently testing, so if that is a safe position, then we can add this position to our current solution. So we can put our current solution, so our current solution for row number 1 will be equal to column 1, which is the current one we're testing. And once we've found that, then we of course need to carry on down and test other rows. If it's not safe, all we simply do is finish our loop, go round, and then check the next column. Okay, so in this position here, so we'll start off, if we just do a bit of a dry run with it, so we come in, our first test position will be row 0, column 0, and again that goes into our solution. We then come down to row 1, so it will be trying a queen in row 1, column 0, and of course that will be directly underneath our first queen, so that will not be safe. So we will simply skip over this and come round and then check for row 1, column 1. And of course that will just be diagonally opposite our upper queen. So again, that doesn't get it. We then come back round and check row 1, column 2. And in that position, the queen we've just placed on row 0 is not attacking this one. So that will be a safe position. We will then log this value of 2 against our row 1 solution, and then we need to carry on down and look at our next row. So you can see that we're sort of carrying on down and following this procedure of creating a for loop which loops through each of the columns, checking if we get a safe solution. If not, we just simply go round again. If it is safe, then we have to carry on down our tree. Now eventually we will get down to the final column in this. So if we come down in here, so eventually, let me just bring this back over here a bit. Okay, so eventually we will go all the way down and we will get to test row 7. So we've now found safe positions in all the upper 7 rows. And in row 7 now we do exactly the same thing. So we put a queen in column 0, test if it's safe. If it's not, we come back round, put a queen in column 1, test if that's safe. And eventually we could get to a situation where we test a queen in one of the columns and it becomes a safe solution. Now we're now on the last row, so in effect we need to store that value, but now our current solution array contains an actual solution to the problem. So at this point here we've actually found a solution, and we then need to do something about that, obviously. So we will need to store a second array which will contain all of the individual solutions. But then we can simply come out of there and then continue testing it. So we might find a couple of solutions on row 7. If not, then this will end, and of course we will then jump back up and continue testing the further row 6 values that we haven't done. So really what we're doing here, we're creating a multi-nested for loop, and that will then take us through every possible combination. But it also means that once we get a certain way down our solution and it doesn't work, we then skip over all of the incorrect ones. So if we get to a situation where, say we had column 0 being 0, row 1 being in column 2, and so on, if we then try row 2, again we can't put anything in column 0, but we don't then go down all the rest of the nested loops. We simply skip over that whole value and then come back out and check the next one. So we're only going as deep as we need to find an incorrect solution, and then skipping over all of those incorrect solutions to check for the next safe one. Okay. So that's our overall structure for our nested looping system. I know that some of you will probably know that we will talk about recursion soon, but for now let's just keep it simple and do it with nested loops. So our algorithm has identified that we need this function isSafe, and that's going to take as one parameter the position that we're testing, and then it will check to see if any of the queens around that are attacking that position. So let's consider that we've got partway through our solution and we've placed our first 3 queens on the first 3 rows, and we've now got to a situation where we want to check this red position to see if it is safe. So thinking about these checks, first off, we only need to check rows that are above our current test row. Any rows beneath this one, we haven't yet placed any queens on there, so there's no point testing those. So instantly we reduce the number of tests we need to do. And then really there are only three possible situations. A queen could be directly above our current test position, and that would mean that its column position would be the same column number that we're currently testing. Or it could be diagonally off and up to the left, or diagonally off and up to the right. And if we think about our diagonal tests, for it to be diagonal, we simply need to count how many rows up we are and how many columns across we are. So really, if a queen on a row 2 rows above us is 2 columns to one side, so in other words, the difference in row numbers and the difference in column numbers is the same, then that's a diagonal attack. And so really, all we need to do is we need to look at the row where we're testing to see if a ready placed queen is attacking, have a look at its row and column number, take away the row and column number of our red test position, and if the absolute values of those, in other words whether it's positive or negative, are the same, then we know that we've got a diagonally opposite queen and it's attacking our test position. And again, by taking the absolute value, so our row difference, so if we take the existing queen's row number away from our test row number, we will always get a positive value. If we then take the existing queen's row number, column number, away from our test column number, but take the absolute value of that, that will again give us a positive number. And then if those two numbers are the same, then we know that it is diagonally in line with our test position and therefore not safe. Let's see if we can write the pseudocode for this function then. So really, if I just paste in a finished version then. So we've got our function is safe. We will need to send it which row we are testing and which column we're testing. So this is where we want to try and place the next queen. So initially then we're going to create a Boolean variable to say that this is true. And then if we find a queen that's attacking us, we will change that to false. So we need to then look at the so from the top row down to one row above our current test row. So for row equals 0, which is the top row. Test row minus 1 is one row above where we currently are testing. We're looking then, so current solution row will give us the column number of the queen that we placed in this row. So if the queen is in the same column as our test column, then we are not safe. And that tests then sort of for vertical alignment. Diagonal alignment, so again, our test row is where we are currently testing. Row is the previous queen that we're now looping through, so that will tell us how many rows above us we are testing. This one here, so our current test column, the column number where the queen above us, remember that we're looping through, is placed on. So if we take that difference and then find the absolute value of it, we'll then be comparing two positive numbers. So one will tell us how many rows above we are, and one will tell us how many columns to the side we are. So if those are equal, then again we are diagonal. So we have a queen attacking us, so we are not safe. So at the end of this loop then, if we have found any single queen attacking us, our safe variable will have been set to false. If we haven't found any queens attacking us, then it will still contain its true value. So when we return that back, that will then give us the true value of whether this is a safe position or not. Now we can actually slightly optimize this bit of code. This will find us every single queen that is attacking us. But we don't need to do that. We really just need to find one. So the very first queen we find attacking us, then we're just not safe, and that's that. So we don't actually need to use this variable. What we could simply say is, if we find a queen attacking us, then simply return back a false value. Okay, so in other words, as soon as we find any queen that's attacking us, we will send back a false value. We are not safe. And again, we'll need to do it here as well. So return false. If we manage to get through the whole test loop and not have found a queen attacking us, then we are safe. So we return back true. So that then gives us a solution then to our isSafe function. Again, you can see it all comes out to be quite simple in the end. So let's actually stick this into some Python code and see if we can actually get our solution to this problem. So I'm in Python here, and we've got a solution then coded out for us. So again, I've set a variable here, numQueens. This problem can be scaled up to any real board size. But again, I'm doing this then for 8 queens. So we create an array for our current solution. And again, that will be then an array with numQueen elements in it. Okay, so at the moment 8. So down here, well, let's take it stage by stage. I'm then creating a second array, which is, or in Python, these are lists, obviously. So a second list, which is going to store copies of each solution that we find. So basically our current solution will be an array, and we will build that up and fill it up. And as soon as we find a current solution, we'll take a copy of that and stick it into our total solutions array. So this solutions list will be a list of lists, if you see what I mean. Okay, but anyway, that's how I'm just making sure that we keep a record of each solution that we find. So this is our isSafe function, and again, it's exactly as we did in our pseudocode. So we send in the row and column that we're testing for. I'm doing a check here, so if our test row, if we're testing in row 0, then obviously that always returns true because every position in row 0 is safe. Then underneath that, then we're then looping through. So if we're not in row 0, then we get through to here, and we will check each of the rows above us for both horizontal alignment and then vertical alignment. Okay, and that's using exactly the same code that we did in our pseudocode. So down here, then again we've got our nested loops. So we're basically saying, so I'm explicitly saying here about the continue side of things. So if it's not safe to put a queen in this position, then just simply go round and do the next position. Else, then we log this current queen and then go down to the next row and do exactly the same. So that's our pseudocode just put out. And as I say, I'm putting in this little clause here so that we can actually see that it is going to just simply loop round. Otherwise, we'd have to have a look down to see where exactly this loop ended down below. Okay, so that's just to make it a bit clearer. So really, we go down through our nested loops, going all the way down, and eventually we get down to our final bottom row. And we're looping through that. So again, we're doing this. So if we haven't found a safe position, then go and check the next position on this row. Else, we have actually found at this point our finished solution. So we log it into our current solution, which we're building up in that array, and then we append that array into our total solutions array. So that then should loop us through there, finding every single combination, checking them out, and then creating an array of solutions. So the last little bit down here is just simply going to tell us how many solutions we found in total, and then print each of those arrays out. So that will then just give us a list of column numbers for each of the rows. So let's just run that and see what happens. So let's come down here, and if we run that, so it comes down, and you can see it actually executes pretty quickly. So we have found 92 solutions to the problem. So our first solution, so on the top row, we have a queen in column 0, then column 4, then column 7, 5, 2, 6, 1, and 3. So that gives us a solution. If we then lay that out on an actual chessboard, putting each queen in its specific column number, we'll see that that actually works. If you have a look through there, you'll see that there aren't any two queens attacking each other. So that gives us the code for one way of solving this. And again, this is using nested loops. Again, I'll include links to all the code for this in the description below, or if you're actually on my website already, it'll be available for download somewhere beneath this video. But as I did say at the beginning of this code explanation, there is the possibility of expanding this out to have an arbitrary number of queens. So the idea here is if we're trying to place 8 queens, we need an 8 by 8 chessboard, and of course that's the normal size. But say we wanted to increase that up to, let's say, a 16 by 16 chessboard, placing 16 queens on it. Well, obviously our code could handle that, but at the moment, the way we've written this, the code we've written is to a fixed size grid, because we've had to add an extra for loop in for each row in our grid. So if I wanted to do 16 by 16, I would then have to come down here, and instead of ending at the 8th row, so index 7 down here, I would have to continue this process down until we get to 4 queen 15. And again, that then becomes very inflexible. I actually have to modify my code if I want to do a different grid size. So the next, the last little optimization for this is we're going to write a general purpose block of code, and we're going to have to use something called recursion for this. And recursion really is where we're getting a function to actually be able to call itself and do the nesting of, so at the moment we've got this nested loops. So our function is actually going to do one loop, but it's going to call itself from within itself to do a loop inside a loop. Now recursion, quite a few people sort of shy away from recursion, but once you get your head round what's actually going on, it's not too bad, and it can become, especially if we are in nested tree situations, so like we are at the moment, or perhaps you were working through a product categories in a website or something like that. Recursion becomes a very powerful tool to instantly simplify what would be an incredibly complex task to achieve without it. So let's have a look at that next. For recursion to work, we need to develop a function, and this function needs to perform one unit of our task. So in our case, that unit is going to be placing a queen on a row. So as the function progresses, it will perform its calculations looking for an answer. So in our situation, it's going to be testing each of the columns in this particular row to find a safe position for a queen. So once we identify this piece of data, we then need to decide whether that involves us delving deeper down into our looping structure. So in other words, if we find a safe position for a queen, then we will need to look and then place a queen on the next row down. Or we might decide that this is some sort of end situation where we then need to start passing information back up the loop to sort of complete this cycle. So in this way, our single function ends up repeatedly calling itself from within itself to build up that tree structure and that nested loop structure that we saw in our previous solution. Again, eventually we get to a situation where we are, in our situation at least, placing queens on the very last row. Okay, so our function will need some awareness of what the last row on how to identify it. And at that point, it will get to a situation where it identifies its safe positions and decides that it no longer needs to delve any deeper down into the recursion. And then we'll just simply start returning its values back. And again, we'll see how we do that in the actual solution. So this is the real basis then of recursion. So we break it down into a unit task. That unit task, as it's calculating itself, understands when it needs to delve down deeper into unit tasks, and those unit tasks then need to identify endpoints when they start returning back out of the recursion and eventually end the system. Looking at the code solution then, it starts off very similar to our previous solution. So we are specifying how many queens that we are solving this problem for. We've then got a global variable which is containing an array which tells us where we've placed the queens so far as we're working through. We've then got another global variable which is going to keep track of all the different solutions that we find. We still need to be able to test a grid square in our board to see whether it's safe to put a queen there or not, and that's identical to the one we had before. So we simply give it a row and a column. It will have a look at the previously placed queens and tell us whether this grid square is safe or not safe. But then we come down to where we used to have our nested loop, and this single function here is now our complete solution. So we have a function which is going to place a queen on a specified row. Now to do that, it's going to need to have access to the current solution that we're building up. It will need to have access to the complete list of solutions, because again, eventually this is going to add something into that complete list of solutions. And of course, it needs to understand the parameters restricting our situation. So it needs to know what the maximum number of queens that we are using is, again, so that it can work out when it gets to the actual end row. So the actual calculation, so again, because we've already been looking at the nested looping situation, we already know what we need to do for a single row. And we basically just need to loop through each column in this row, check if this row and column position is safe or not. So if it's not safe, we just simply loop round and try the next column. But if it is safe, again, we need to make a note of this safe position in our current solution. And then we need to decide whether we are going to recurse and go down to the next level, or whether we've actually come to the end of this recursion. So if we are on the last row, so this if statement here, so if the current row that we're looking on, the index of that is num queens minus 1, so that's the final row, then we have actually got a actual solution to the problem, and at that point we're going to save that. But if we're not on the end row, at that point we need to now recurse down one more level. So we're going to call this function again, but we're going to call it with the index of the next row. So we will now be recursing down, calling our function, and be trying to place a queen on the next row down. Once that then, so eventually this function call, it will then recurse down as far as it needs to go. Eventually it will come back out again, so we will have found a solution or not. It will come back out again, and we will then simply return from this version of the function. So in effect, we are calling our function, we're then starting to loop round. Eventually this loop will come to an end, and at that point this level of recursion will return and return control back up one level, so that that level can then complete its loop round the number of queens, finish off and return back up again. So eventually we will then start to backtrace and jump up the loops back up to the beginning. So that's the basic method in which our recursion works. So we need to come into our recursion with an idea of what we're doing, have access to certain blocks of data, decide whether we need to save a solution and get out of here, or whether we need to delve deeper down into the recursion. So to get the whole process started, we of course need to make our first call to our recursive function. And we simply need to say, try and place a queen on row 0, and that will kick off the whole process. So eventually this function call will have delved down through all the various solutions, and we will have got a return from it. And when we return from it, we know that our global variable solutions will contain a list of all of the possible solutions that we found. So let's give it a go and see what happens. So we come in here, let's run our recursive function. And there we have again our 92, if I get to the top here. Our 92 solutions, and again that is the same initial solution that we found the previous time. So really what I want you to take from this is that yes, recursion you do need to get your head around this idea of the unit task and how that unit task builds up its data and then decides whether it needs to recurse further or then start to get out of the recursion. But once you've got that worked out, hopefully you can see now that our solution to this problem is actually very, very simple. So what seemed like quite a complex task of placing queens on a board so that they don't attack each other has now become down to very much about 30 lines of code. And again, our recursive function here is doing a lot of our work. So in itself, the function is not very complicated. But when you add it into this idea of recursion and repeatedly calling itself from different situations, you can see how that expands out into quite a large block of code if we were to write out everything it was doing. Now this solution obviously then means that we can now adjust the number up here. So our solution is aware of how big our grid is. It always will use the single unit function. So we no longer have to now modify our code by adding in extra loops to cope with the extra size of our grid. We can simply come up here and we can adjust this number. So we could have said, let's try a 10 by 10 grid with 10 queens in it, and let's run that and see what happens. And again, we get a solution in quite short order. So now we have found 724 solutions, and I'm sure if we were to plot this out on a 10 by 10 chessboard, we would find that works. So that's a solution to this 8 queen problem. If you're interested in learning more about Python programming, then please do check out my Python courses. I'll put some links in the description below. If you're studying computer science at school, then Python is very probably the language that you're going to be learning, so do check those out. Also make sure you have a look at my website. There's lots more information on there and different ideas on computer science and programming. And of course, make sure that you click that subscribe button down below, turn on your notifications so that you don't miss any more of my videos. So I hope you've enjoyed that, and hopefully I will see you soon. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.